Welcome to the deep dive. Today, we're really getting into the nitty-gritty of how stuff works chemically.
Yeah, we're looking at chemical reactions, not just abstract ideas, but actual experiments you've shared.
Exactly. We've got this great mix, things like, metals fighting over oxygen, ink that just vanishes.
Mm-hmm. And crystal gardens growing, particles mixing.
It's quite a range. Stuff happening in crucibles, jars, test tubes. It really shows you that chemistry is happening everywhere, in all sorts of ways.
And that's our mission for this deep dive, isn't it?
Yeah.
To look at these different experiments, these snapshots, and pull out the really interesting bits.
Right. We want to understand the why behind what we see, the core ideas, but without, drowning in technical jargon.
Precisely. Making sense of the transformations.
Okay, so let's kick things off with that first idea, competition for oxygen. It sounds almost like elements having a brawl.
Huh. Well, it kind of is. It's a fantastic way to see reactivity in action.
Yeah.
You basically pit a metal against a metal oxide.
And the more reactive one, it wins. It grabs the oxygen.
That's the idea. It forms its own oxide. We're looking at specific mixes like magnesium oxide and iron.
Lead oxide and iron.
Lead oxide and zinc. Iron oxide and zinc. And the key is just watching. Does something happen when you heat them?
So the observation tells you which metal is, let's say, more eager chemically.
Exactly. It's about relative reactivity. You see a change, reaction occurred, and the more reactive metal muscled this way in.
It's quite direct. And of course, the usual safety reminders, eye protection, don't hover over the hot stuff.
Always.
And asking for the word equations for the reactions that do happen really forces you to think about what's actually changing, what new substance is formed.
Yeah. What are the products?
Yeah.
And this idea of taking oxygen, it leads straight into the next set. Extracting metal with charcoal.
Right, so here it's carbon getting into the ring.
Exactly. Is carbon versus a metal oxide. If carbon's more reactive, it can pull the oxygen away.
Leaving the metal by itself.
Like carbon has a stronger grip on the oxygen, you could say.
And we see this with lead oxide and copper oxide in the sources.
Yeah. For lead oxide, you mix the powders, heat them strongly in an ignition tube.
And look for that little glint of metal.
A trace of metal, yeah. That tells you carbon 1. With copper oxide, it's slightly different. You layer them.
Without mixing.
Right. And then you focus on the boundary, the interface, after heating. See what happened right there.
Interesting, like watching the reaction zone.
And the questions push deeper. Why cool it before tipping?
To stop any further reactions, maybe? Freeze the evidence.
Sort of, yeah, to observe it at that specific point. And what happens to the carbon if it takes the oxygen?
It gets oxidized, right? Forms carbon dioxide or monoxide.
Precisely. And then writing the equation for the lead oxide reaction, identifying oxidation and reduction, that's mapping the whole process.
Reduction being the metal oxide losing its oxygen.
You got it.
Okay, and that connects directly to reducing iron oxide with carbon.
It reinforces that whole reactivity idea. Carbon can reduce oxides of metals that are, let's say, less reactive than zinc, but more reactive than copper. It sits somewhere in that hierarchy.
And the experiment is neat, charring a match for carbon.
Simple source of carbon.
Mixing it with iron oxide, heating it, crushing the result, and using a magnet.
Yeah, the magnet's the clever bit. If you've made elemental iron, the magnet will pick it up. That's your proof of reduction.
A simple test for a fundamental change. And again, the questions push us to define reduction, place carbon in that reactivity series, potassium, sodium, calcium, all the way down to copper.
And crucially, why can't carbon reduce something like calcium oxide?
Because calcium is way up there, holds on to its oxygen much more tightly.
Exactly. Calcium's bond with oxygen is just too strong for carbon to break. It's all about that energy hierarchy.
Okay, powerful stuff, these oxygen battles. Let's switch gears a bit. What about making things like the crystal garden? That sounds lovely.
It looks lovely. And it draws this really neat parallel to how silicate minerals form deep in the Earth's mantle, involving silicon dioxide and metal oxides at immense temperatures.
But the lab version is gentler.
Much gentler. You dissolve sodium silicate that's like water glass in hot water, let it settle, and then drop in tiny crystals of different metal salts like nitrates or sulfates.
And just watch.
Watch what happens overnight. You get these beautiful branching structures growing upwards.
Like underwater plants. And the colors, they come from the metal.
Yes. The different metal ions give the different colors. Copper salts might give bluish structures. Iron salts maybe reddish or greenish.
And why isn't this the same as the Earth's mantle then?
Well, think about it. Down there, you've got crushing pressures, extreme heat, completely different conditions that affect how things react and what structures form. The garden is an analogy, a glimpse, not a perfect replica.
Right, conditions matter. Okay, next up, metal oxides reacting with acids.
Another really common and important reaction type. Many metal oxides act like bases.
And neutralize acids.
Exactly. The experiment uses copper A oxide and dilute sulfuric acid. You heat the acid gently, add the black copper oxide powder bit by bit until no more dissolves.
So you know you've used up all the acid or reacted as much as possible.
Right. Then you filter the hot mixture.
Okay, so what's left on the filter paper?
That would be the unreacted copper oxide, the solid that didn't dissolve.
And the liquid that goes through the filtrate.
That contains the product, copper 2 sulfate, which is soluble in water. It's a blue solution usually.
Ah, so the acid and the oxide made a salt and water, essentially.
Yep. Copper 2 sulfate is the salt here. And the question about getting the solid product out of that filtrate.
You'd have to evaporate the water off, right? Carefully heat it.
Precisely. Gentle evaporation leaves the copper sulfate crystals behind.
Cool. Okay, now for the one that sounds like magic disappearing ink.
Yeah, this one's fun. You make a blue ink spot on paper, and poof, it vanishes.
Oh!
It's clever chemistry involving air. The ink is ethanol mixed with an indicator called zymolphthalin.
An indicator, like litmus, changes color based on acid or alkali.
Exactly. Then you add just enough sodium hydroxide, which is an alkali, to make the solution alkaline. And in alkali, thymolphthalin turns deep blue.
Okay, so the alkali makes it blue, but why does it disappear?
The sodium hydroxide reacts with a gas in the air.
Not oxygen this time.
No. Think about what else is in the air that might react with an alkali.
Carbon dioxide?
Bingo. Carbon dioxide, even though it's only a small part of air, is slightly acidic. It reacts with the sodium hydroxide.
Neutralizing it.
Gradually, yes. As the alkali gets neutralized, the solution becomes less alkaline, and the thymolphthalin indicator switches back to being colorless.
So the blue fades away? That's brilliant. It's the CO2 in the air doing it.
A great demonstration that the atmosphere isn't just passive, it's chemically active.
Wow. Okay, from disappearing ink to tiny invisible things, experiments with particles, and particles in motion.
Yeah, these get us thinking about matter on a microscopic scale. The first set looks at volume changes when you mix things.
Like peas and sand.
Peas and sand, yeah. Or alcohol and water. Or dissolving salt in water. The point is careful measuring volume at eye level.
And the volumes don't just add up, do they?
Not always. With peas and sand, the smaller sand grains fill the gaps between the bigger peas, so the total volume is less than you'd get just adding the two separate volumes.
Okay, that makes sense. It's like fitting things together better. What about alcohol and water?
Similar idea, but with molecules. Alcohol and water molecules attract each other and can pack more closely together than when they're separate. So 50 milliliters of alcohol plus 50 milliliters of water gives you less than 100 milliliters of mixture.
Huh. That's counterintuitive.
It really shows that particles interact and arrange themselves. And dissolving salt in water. The volume increases, but usually not by the full volume of the solid salt you added.
Suggesting the salt particles are slotting in between the water molecules?
Exactly. It all points to this idea of matter being made of particles with spaces between them.
Which leads nicely into particles in motion, testing if gas particles move.
Right. If solid and liquid particles are arranging themselves, what about gases? This experiment uses carbon dioxide. You make some.
Calcium carbonate and acid.
Yep. Collect the CO2.
Yeah.
Then you take a test tube of CO2 and invert it over a test tube of air and do the reverse too, air over CO2.
And wait?
Wait a bit. Then test both tubes in each pair with lime water.
Lime water goes cloudy if CO2 is present. So what are we expecting?
Well, CO2 is denser than air, so you might think it would stay in the bottom tube.
But if the particles are moving randomly,
they should mix, even moving upwards against gravity. And that's what you typically find. CO2 spreads into both tubes over time.
So even though CO2 is heavier, the random motion diffusion mixes them up.
It's strong evidence for the kinetic theory of gases. Particles are constantly moving and colliding. You see the result of the motion.
Very clever. Okay, different kind of movement now. Charged particles. The migration of ions.
Yeah, this touches on electrolysis. When some compounds dissolve in water, they form ions, charged atoms, or groups of atoms.
Positive and negative ions.
Right. And if you apply an electric current, these ions move. Opposites attract. Positive ions go to the negative electrode. Negative ions to the positive electrode.
And the experiment shows this.
Part 1 does, beautifully. Use a potassium manganate. It has this intense purple manganate ion.
So you can see it.
You put a crystal on wet filter paper connected to a power supply, and you literally watch the purple color spread towards one of the electrodes.
Which tells you it's charged.
Exactly. If it moves to the positive electrode, the ion must be negatively charged.
Simple and visual. What about part 2?
Part 2 shows ions meeting and reacting. You use two different solutions, silver nitrate and potassium chromate, put them on different parts of the wet filter paper.
Okay, so the ions start migrating towards each other.
Yes. Silver ions, Ag+ from one, chromate ions, Cr4d2 from the other. And where they meet in the middle,
Something happens.
they form an insoluble solid silver chromate, which is bright red. You see this line of red precipitate forming where the invisible ions met and reacted.
Wow. So you see the result of the ions migrating and then combining.
That's what
Precipitation.
Exactly. And again, safety silver nitrate stains skin black. Potassium chromate is toxic. Handle with care.
Good reminder. Okay, last one, back to basics almost. Making a pH indicator from red cabbage.
Yeah, this is fantastic, really accessible chemistry. Red cabbage juice changes color depending on whether something is acidic or alkaline.
Because of natural pigments.
Anthocyanins, yes. You just boil some cabbage in water to get the color juice.
And then test it.
Add it to a known acid, a known alkali, and some neutral water, like deionized water.
And you see different colors.
Definitely. It's typically reddish pink in acid, greenish yellow in strong alkali, and purplish when neutral. It gives you a visual scale.
So you could use it to test other things, like lemon juice or baking soda solution.
Absolutely. It's a natural homemade pH indicator. Shows that chemistry isn't just for labs with fancy chemicals.
That's a great one to end on. So looking back, we've covered a lot of ground.
We really have. From reactivity and who gets the oxygen,
To making crystals in ink that vanishes.
thinking about particles moving, whether they're tiny molecules or charged ions.
And using cabbage to tell acids from alkalis. It really ties together, doesn't it? These different experiments all show fundamental chemical ideas at work.
They absolutely do. And hopefully you start to see the connections, like how that disappearing ink relies on a gas from the air, which connects back to the idea of particles in motion.
Right. Or seeing those colored ions actually move feels quite real.
Tangible results from invisible processes.
So a final thought then. We saw metals battling for oxygen. It makes you think, where else, maybe in nature or industry, do we see these kinds of competitions for resources playing out on a chemical level?
That's a great question. Or thinking about the cabbage indicator, what other everyday plants or foods might hold similar chemical secrets, acting as indicators, or having other interesting properties we just haven't noticed.
Lots to ponder. Well, this has been a fascinating deep dive into the world of reactions. Thanks for joining us.